We take a look here. The question we have is going to be about the effects of stress on a femur, the femur of a human being. The important thing to remember is our three equations. Stress, which is how hard the load works to actually change the shape of your object, is equal to the force acting on that object divided by the cross-sectional area. The strain is just the ratio of the change in length of your object to the initial length of your object. And these two, stress and strain, are related through what's called Young's modulus, which is just the ratio of stress to strain. Now really quickly, just to recap a stress-strain diagram, as the stress is being increased, as that load is being increased on your object, the strain increases as well. If you remember, there is one section of a stress-strain graph where the data is linear, after which it begins to curve and eventually reaches a rupture point. We're concerned with what we call the elastic range. Right up to somewhere about here is where it's no longer linear. As long as I don't apply a stress greater than somewhere right about here where it begins to curve, if I remove that stress, it's still in the elastic range and my object will return to its original shape and it will not be deformed. So that's a quick refresher on the equations as well as a stress-strain curve. If we take a look at the question, it says, given the stress-strain curve shown for various femurs, calculate the maximum force a healthy 21-year-old's femur could withstand without permanently deforming. The radius of the femur is 0.02 meters. Also, we're given that the femur is 0.48 meters in length. So if we want to take a look at this, what we're going to have to start to do is list what we're given. So we know that we're given an area of a radius. The radius is 0.02 meters, which therefore allows us to calculate our cross-sectional area, which hopefully we remember is pi r squared. So pi times our radius, square that, and if we plug that into our calculator, we get pi times our radius squared should give us 0.001. 0.001 square meters. So now we have, I'll move this out of the way, now we have our cross-sectional area. And if we take a look at this diagram right here, we can also see that if we read this, well, if we assume this is somewhere right about where the elastic range ends, we should already just be able to go over it and figure out that since this is 3 and this is 2, right at about 2.5 megapascals is actually our stress, the maximum stress within the elastic range. So we should be able to know that our max stress for the elastic range here is about 2.5 megapascals. And megapascals is, the prefix mega is just 2.5 times 10 to the 6th. So we now have our stress. We also have our cross-sectional area. So if we have our stress and our cross-sectional area, we should be able to find the overall force, or the maximum force, that this femur can withstand without permanently deforming. Any force greater than what we're about to find would exceed the elastic stress, and any deformation would begin to be permanent. You would not return to your original shape unaffected. So if we take a look now, our max force, we rearrange the equation, should be our stress times our cross-sectional area. And we know that our max stress is 2.5 times 10 to the 6 pascals times our cross-sectional area, which is 0.001 square meters. And if we go ahead and take a look at this, 2.5 times 10 to the 6th, and we multiply that by our area, we should wind up with 2,500 newtons. So that's the maximum amount of force that our femur, or this 21-year-old femur, can withstand before any permanent deformation is going to occur. Anything less than or up to 2,500 newtons, as soon as it's removed, that femur will go back to its original shape. So we've answered the first part of the question. The next part that I would be interested in would be, what is the overall change in length of the femur under this maximum force? So hopefully, if realize now if we want the change in length, we're going to need to use our strain equation. So we take a look again at our graph. Well, we know right around here is where our elastic range ends. We already read the stress before. We should also be able to read the strain, which right around here looks like it's about 5. So if our strain, or the max strain, is 5%, be careful, it's 5%. If it's 5%, then it should equal 0.05. So if our strain is 0.05, then what we need to do here is take a look at our strain equation. Our strain is going to be equal to our change in length over our original length. And then all we're going to have to do is calculate what our change in length is, which should be 0. Oops, I apologize. Get this out of here. Should be 0.05 times 0.48. If we plug this in, where'd my calculator go? Bear with me. If we plug this into our calculator, we should get 0.05 times 0.48. And what I should wind up with is 0.024. meters. So by just reading the information off of our graph and taking a look at the equations we're given, we should be able to figure out at this point the maximum force as well as the change in length of this femur at that point. The last question I want to ask here is, what is Young's modulus for a healthy 21-year-old's femur? Hopefully at this point you realize, again, Young's modulus is just the ratio of stress to strain. So we take a look at our graph. Well, Young's modulus at this point is going to be the slope of that section. So if we look at our elastic range, as we said before, our stress would be about 2.5 megapascals, which is, our stress is 2.5 times 10 to the 6th. Our strain, as we read from the bottom, is about 5%, so 0.05. And these two are related because they're very simply the ratio. 2.5 times 10 to the 6th over 0.05. If we plug that into our calculator, 2.5 times 10 to the 6th. We divide that by 0.05. We should wind up with is somewhere around 5 times 10 to the 8 pascals. So the important things to remember here are very simply that when you're looking at your stress-strain graph, you have the elastic range, which is what we're generally concerned with. Young's modulus is just the ratio or the slope of that linear elastic section. The strain is quite simply the change in length over the original length, so you can use that to find your change in length or your final length. And stress is the ratio of force to cross-sectional area. So by using these two equations, you can analyze the actual deformation of your object, in this case a femur, and if you need a way to relate the two, it's Young's modulus.